Hello everybody, this is Mr. Linares. I'm going to go ahead and make a little helper video here. A few students brought to my attention that some of the modules in Electude assume you know a few things that you have not been taught. I'll say this, some of the modules that are related to this do go over the material a little bit, but there is a tool called the digital multimeter that we have not covered yet because we haven't covered electricity. And what I'm going to do now, I'm not going to cover electricity in its entirety, or go over a full course of it, but I am going to give you some of the basic ideas that are necessary for you to get through the modules. This is also act as a primer for learning electrical later on, as well as learning how to use the tool, the digital multimeter, sorry for the stutter, the digital multimeter in order to get things set up with Electude, because the little graphic they use is somewhat different than what you experience today in the real world tools. Only reason I say that is most of the tools you have now operate automatically. This one has you make very specific selections. So here we go. We're going to go over some terms. After we go over these terms, I'll run through one of the modules just to give you kind of the heads up about it and how to use the terms, remind you about what I'm going to cover here on the whiteboard. Okay, so hopefully this won't take too long, but if it does, it does. We need to learn this. Okay, here we go. Let's see here. Let me give a little pause right here for a second. I got to clear something off my desk. All right, here we go. So when we're talking about electricity, there's a few ideas that we've got to go over. And the first one is what's called Ohm's Law. Okay, I'm going to give the basic shakedown on Ohm's Law, the very simple way that I teach it, even up to my college classes. Okay, and then as we go through Ohm's Law, we'll be able to talk about the values that we're going to be discussing in Ohm's Law. Okay, so here we go. Actually, I'm going to type this out so it's much clearer than I could write. And then we'll just scoot that over here so we have it nice and pretty. 1 volt of electrical pressure will push 1 amp or 1 ampere of electrical current through 1 ohm of electrical resistance. At its most basic, this is Ohm's Law. Okay, now let's go over this. 1 volt of electrical pressure will push 1 ampere of electrical current through, oops, hey, we got a bad number there. You see that? That would have been a hell of a thing to leave up, huh? Through 1 ohm of electrical resistance. Once again, 1 volt of electrical pressure will push 1 ampere of electrical current through 1 ohm of electrical resistance. So what we have going on here is 1 volt of electrical pressure will push 1 amp or 1 ampere, we say amps, okay, of electrical current through 1 ohm of electrical resistance. Volts pushes amps through ohms. Pressure pushes current through resistance or past it. Okay, pick your idea here. Okay, so volt is pressure. Now we also call volt, it's a volt is a measurement of voltage, and voltage is electromotive force. This is the force that moves electrons. Okay, we make this happen by having more electrons on one side of a power source than the other, namely a battery. Okay, and this is just to get you started for right now, okay? There's more to this. So let's say on one side of the battery, I've got a lot of extra electrons hanging around on a piece of metal, okay? And on the other side of the battery, I've got another piece of metal without a lot of extra electrons, okay? What'll happen is when I connect a circuit between either side of these batteries, those electrons, realizing that there's a conductive path to go from positive to negative, okay, will be motivated to move, right? The attractive forces of magnetism come into play, positive and negative, polarity, things like that, in order to get electrons moving from atom to atom through a conductor, okay, to make it to the other side of the power source. This is the chemical makeup of the battery, or the magnetic makeup of your power source, trying to balance forces out, okay? That difference in forces on one side or the other makes a difference in potential, a difference in pressure. That pressure is what's moving electrons from atom to atom through a conductor, okay? What is being pushed are electrons, and that flow of electrons is called current, okay? Oops, I misspelled the hell out of that, didn't I? Amperage, which is current, okay? Flow of electrons from atom to atom through a conductor. In our case, we're talking about copper wire typically, okay? Or pretty much any metal, most metals, okay? Things like wood and plastic, okay? Most air, most water are going to be insulators, all right? Now, ohms, oops, there's no apostrophe there. Ohms is just resistance to flow. What a material is made out of, okay? A conductor, they have low resistance. Very, very low resistance. Insulators have high resistance. Okay? Now, these values are subjective. You will learn them as you just carry on through the automotive world. Okay? Now, let me draw a little circuit just to get a little basic idea across to you. Okay, just draw a simple little light bulb. I'm going to go ahead and erase this, so you can always just rewind it up, freeze it, screenshot it, whatever you need to do. I'm going to clear out this. I'm going to leave Ohm's Law right there because that's a constant reference we're going to have. Okay, so let's go ahead and draw a little circuit. I'll explain the parts here in a second. If anyone's had electronics before, you realize how incredibly simplified what I'm doing is. There's a very good reason, and that's just because we're teaching ground level basics here, okay? So we have 5 parts to a circuit. First, we have conductor. No conductor, no circuit. That's our wire, okay? Anywhere you see a straight black line in here, okay? Here, 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 right here, right there, and right there. You're going to be having, you have your conductor, okay? 2, your power source. 3, a method of protection. In the case of automotive circuits, this is typically a fuse. Okay, there are circuit breakers like you have in the house and other types of wire that are specially designed to protect circuits. We're not worried about that right now. for right now, we'll just work with fuse, that little squiggly with the two dots. Okay, it looks like a little bit like a tilde, right? Dot, squiggly, dot. That's going to be a fuse, okay? Fourth thing you're going to have is a control. This, generally speaking, is going to be some kind of switch. And that's what's right here, okay? Last thing you're going to need is something to make use of the electrical power, okay? And that is called a load or a consumer. Consumer, for our level, is probably the easiest way to understand what I'm about to talk about. However, load is a little bit more common in the auto industry, okay? So let's go with this. First, we have our wire, okay? And this wire, the conductor, is going to connect all of the remaining parts. So we have, let's go ahead from the beginning and end of the circuit. The power source. Power source has got a positive and negative side to it. Everything that's on this side of the battery, that's what this little symbol is here, is going to be on the positive side. Anything that is towards the negative side of the circuit is going to be negative, okay? So let's go on. First, we have our battery. Let's say our battery makes 12 volts, 12 capital V, 12 volts, right? Now, in a circuit, all this energy is going to be consumed, all this voltage is going to be consumed, used up between the positive and negative, all right? This pressure is going to be applied to the circuit, and all this pressure will be expended, okay? It doesn't matter if you have 1 light, 12 lights, 34 lights, in a motor, okay, an electromagnet, whatever you got going on, okay? That's the rule. All the voltage will be consumed in a circuit when it's connected. Right here is our fuse protection. This is protecting against high current flow, okay? If the flow of current goes too high, there will be heat generated, and that heat will melt open the fuse, okay? This will fail and melt open, melt apart, melt so there's no more connection to protect the rest of the parts in the circuit physically. We eventually come to our switch, which opens and closes the circuit. Open is when it is not connected. Closed is when it is connected. Open circuit, closed circuit, off, on. Then we have our load. This is what's going to be using up the voltage, okay? Now, the reason we have to have a load in the circuit is if we don't have any resistance, okay, or much resistance, our current is going to go too fast, cause too much heat, and burn things down, okay? Literally burn the circuit apart. So let's go ahead and let me clean things up a little bit because we're about to get on with some numbers here. Not too much. Oh, the system decided to draw perfect circles for me. Lovely. Okay. Hang on a second. I'm going to get rid of these because I have to switch devices real quick. Doesn't work with the pen. Okay. Now, just to have a number, doesn't matter what number really we're going to pick at this level, but we're going to pick a number. And let's just use 3. This little horseshoe symbol is ohms. 1 ohm of resistance here. The symbol is the omega symbol. Looks like a horseshoe. 3 ohms of resistance, 12 volts here. This is where learning Ohm's law comes through, because 1 volt of electrical pressure will push 1 amp of electrical current through 1 ohm of electrical resistance. Looks like an algebra problem might happen. I did not give any rules about the relationship between these 3, only this information. So this information here means that a single value of any of these is going to relate to the others at that same rate. Check this out. I'm going to draw a little circle. At least it was nice enough to me to do that. Sometimes it doesn't draw it out for me. V for volts, A for amps, R for resistance. We put a little multiplication X here. two little division symbols here. This is Ohm's Law Pi, okay? It's just a math tool for learning Ohm's Law, okay? There is more to this, I assure you, okay? But for our simple explanation we're having right now, this is gonna cover it. Give me a second here. I need to get a little drinky poo, hang on. Okay, so I have my volts, I have my ohms, I'm missing my amps. If I'm gonna look at this right here, I can figure out which math problem I need to do in order to solve my missing value here. So I have 12 volts, 12. I have 3 ohms here. 12 divided by 3 is what? It's going to be 4. So I'm going to have 4 amps flowing through my circuit. I like to draw a little arrow to indicate that it is flowing, okay? That's just me, though. It doesn't like you're going to see this in any other class necessarily, okay? So I have 12 volts, 3 ohms of resistance, means I could push 4 amps through it. Amperage will not change by itself. The two values it can change by themselves are volts and ohms. Temperature may affect a material, causing it to change resistance, okay? A position might change resistance, all right? Voltage, we all have experienced times where our batteries start to die out and we can't operate our phone anymore, or a flashlight is dying or something like that and the lights go dim, okay? If a power source starts to fail and it doesn't fail outright immediately, the voltage is going to slowly drop, okay? So you may have 10 volts pushing some amperage through 3 ohms, and you'd have to redo this again, okay? In a car, however, we got a little bit of a different system that keeps us constantly charged, however. And talk for another day on that, okay? So, 12 volts, 3 ohms, 4 amps, okay? 12 divided by 3 equals 4. Not a problem there, right? Let's just do another one to show a little something here. Watch this. And I'm going to make a point about this here in a second. So let's just say, let's get rid of my ohms value here. Get rid of my amps value. I'm going to leave that 12 right there. It is a very common basic number we use to teach automotive electrical. Let's go ahead and get rid of these values here. And for the sake of having a number, okay, let's just go ahead and put 6 ohms right here, okay? Now if I put 6 ohms right here, that means my resistance value went up. But check this out. 12 divided by 6 is 2 amps, right? So that meant that if my resistance went up, my current flow went down. So I could go like this, make a little teeter-totter right here, right? If my voltage remains constant, unchanging, and I drop my resistance, okay, my current is going to go up. Likewise, if my voltage remains constant and my resistance goes up, my flow is going to go down. This is very much like a water hose, the shower spigot, your blood, breathing, air hoses, anything like that, okay? If you have got a constant pressure and you change how much resistance is in the flow path, you're going to get a change in your flow, no matter what it is, all right? Now, oh, hang on, I gotta pause. Okay, so back to it, I apologize. Daughter came home from college, had to say hey. Okay, so let's go over this one more time because while it was instantaneous for you, there's been a few minutes for me. So if my volts stay same, if my voltage remains the same and unchanging, okay, and my resistance drops, my flow goes up, my amperage goes up. If my volts remain the same and my resistance goes up, my flow will go down. Now to add to this, so let's go ahead and do this. I have my ohms here, sorry. Well, it's just not very good. Let me fix that. I think so we can see a little bit better. So I have my ohms. Now, think about this like this. If I've got my volts right here, and over here I have my amperage. Now, if my resistance stays the same, it stays unchanging, and I increase my pressure, I push harder, okay? The pathway stays the same, but I push harder. My resistance stays the same, but my voltage increases. That will increase my amperage. That will increase my flow. So if the pathway stays uniform, does not change, and my pressure increases, my flow will go up. If my pathway stays the same, if my resistance remains the same, and my pressure drops, my flow will go down. It will decrease. Okay? These relationships are inviolable. Okay? Rules of the universe kind of stuff. Okay? So now, before we carry on, I'm going to talk about a tool real quick. And then once I talk about this tool, then we're going to go into the electrode thing real quick, and I'll explain how to use the thing in the electrode. Okay? So let me erase a lot of this so we make some more room. Okay? Okay, let me get rid of a few things here. Okay, and I can get rid of that now. So here we go. Let's go ahead and go back to our circuit, draw it a little bit larger. Okay, we have power source, fuse, switch, light bulb, and then ground. Okay, so the positive side of our circuit, negative side of our circuit. And just to have numbers to work with, so we have 12 volts right here. Okay, let's go ahead and pick 2 ohms, which will give us 6 amps right here. 12 divided by 2 is 6. And now we're going to talk about the meter, the digital multimeter, right? So we've got our handy dandy multimeter here. That came out really poorly, didn't it? So here's our meter. It's got a little window. It gives you readouts. Okay. And it looks like a really square Among Us character. Huh. Okay. So now on our meter we have different ports. One port we'll have that we're going to be using anyway is for volts and ohms. Okay. Another port that we're going to be using, usually right nearby it, is for ground. Okay. And you have leads that come out of here. These are, when you hear the term leads, it usually refers to some kind of probe or wire. Okay. Now what's going to happen here is, you see this meter here. I'm going to be writing values out here that will go on the meter where you would set it. Otherwise we'll be in my poor drawing hell for the rest of this. I don't want to do that to you. Okay, so we're going to measure these 3 different values here. Okay. And the first one, most common, most important, is if you're going to be measuring voltage. So you want to measure voltage with your DMM, digital multimeter. When you turn it to volts, you're making it a voltmeter. Generally speaking, in the automotive world, it will look like this. Volts with these straight lines above it to indicate direct current. More about that when we start learning about electricity, okay? And what you'll do is, if you want to measure voltage somewhere in the circuit, let's say you wanted to measure your battery. You get your meter, and you would just go from negative and positive with the meter, and you would get a reading. And you would measure your voltage. Let's say you wanted to measure how much voltage the light bulb was using. Okay, you would get your meter, come on down over here, either side of the bulb, and you would read it. It'd be consuming 12 volts in this instance. Okay, this is called measuring a voltage drop. How much voltage was consumed? How much voltage dropped between the two leads? Now, let's say you wanted to check how much voltage was available at a certain spot, okay? What you would do is you take one lead of your meter and you ground it, like the negative lead. You take the other lead and you could probe anywhere you wanted in the circuit. If you probed at the battery, you would find 12 volts. If you probed at the fuse, you'd find 12 volts. If you probed at the switch, you would find 12 volts. If you probed right after the switch, you would find 12 volts. If you probed at the bulb, you would find 12 volts. If you probed after the bulb, you would find 0 volts because the bulb consumed the voltage. It ate it up. It used up the pressure to get the flow through it, okay? This is called checking for available voltage. The difference between this one and the last one is that this test measures how much voltage could be consumed, and a voltage drop measures how much has been consumed, okay? Same tool, same connections, okay, in terms of how you hook it up on the meter, but where you put it in the circuit, how you apply it, will determine which kind of these tests you're doing. We'll learn much more about that when we cover electricity. I have to redo some of this. Oh well. Not hurt my feelings. I always can just draw it back. Get rid of that. Let's rebuild our circuit real quick. So we've got 2 ohms. Got our 12 volts, 6 amps flowing through. Let's just go ahead and say it is time to measure resistance. So now I'm going to go onto my meter. I'm going to find the ohms value. Now, particular case, this goes for volts and ohms and amps. You need to find the practical range for what you're going to be measuring. Most meters today will auto range and tell you, it will set themselves up automatically for the most visually easy reading you could get. The meter you will see in the electude modules makes you choose a range. So you kind of have to know a little bit about what you're looking at before you set it up, which is a little unfair because they don't set up a standard which way to do the order the modules in. Okay, so bottom line, if you start seeing like dashes in the meter where it's just indicating the meter's telling you I don't see anything, just click up through the ranges. You should have a 200 range, a 2000 range, 2 kilo ohms, 2K ohms, okay? You should have a 20,000 range, okay? You should have a 2 mega ohms or 2 million ohms, okay? And then it goes on up. And the same goes for the voltage ranges as well, okay? Although you're not going to be measuring millions of volts anywhere. If you applied that to something where you and touched it, you'd cook yourself, okay? Let's go ahead and fix our little bulb here. That's got 2 ohms. I want to find out if it has 2 ohms. So I set my meter to ohms. I have to make sure that I disconnect the part that I'm measuring from the circuit, because all these 5 parts of the circuit that make the circuit work, okay, are being taken over by the meter. The meter's got to take care of the power, the protection, the switch, and the wiring. The load is still whatever it is you're measuring. So you get your ohm meter, okay? and you go ahead and you bring one lead to one side of the device you're measuring, or the part you're measuring, and you take the other lead, put it on the other part. You read your 2 ohms, and on the meter in the screen here, it would tell you 2 ohms. Okay, as long as you're in the correct range, and you're going to be fine. Now that's something very, very important to remember when it comes to measuring resistance, is that whatever it is you're measuring must be disconnected completely from the circuit it is part of. Okay, there is no live, no current flowing, no voltage applied measurement for resistance that you would do. Okay, not in any practical application. Now this last one here, oops, I thought that was eraser. This last one here, this has you read amps. Now, amps has A, so there's going to be a little socket that says A for amps, all right? And it'll generally on the meter, it's going to be red, okay? But I'm just using blue because I like to use blue for amperage, okay? What you would do is you're going to go ahead and erase your, well, not erase, you want to erase it. You're going to remove the little lead out of the volts ohms jack, and you would go ahead and take it on over and put it in the amp jack. Keep in mind, you must keep the amount of amperage that you're going to measure with a meter by itself less than 10 amps. Not 10 amps, less than 10 amps. So 9.999999, you're okay. At 10 amps, the internal meter fuse will blow, okay? This is its circuit protection. So when I want to measure the current flow in this circuit, okay, generally speaking, anywhere I measure it in the circuit, I'm going to measure that flow. The 6 amps is present here, 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 here at the light, after the light, and way over here, okay? The amperage doesn't get used up. The pressure gets used up. This pressure is used to move this flow through this resistance back to the battery, okay? All these extra electrons that are on the positive side are going to go ahead and flow through the circuit and go over here to the negative side, all right? And for those of you who understand that what I said is technically incorrect, we have to talk more about that later. Automotive world works positive to negative, okay? There will be more on that when we start discussing electricity in general, okay? So here, we're gonna make an amperage measurement. Now, if I wanna measure the flow of something, I have to get in the flow to measure it, okay? So let's just go ahead and do it at the bulb just because it's an easy area right here. I'm going to go ahead and disconnect my bulb. Okay. Then what I'm going to do, get my ammeter going here. I'm going to run my negative lead, my COM lead, to the negative side of the circuit. I'm going to move my positive lead to the positive side of the circuit, and I make the meter a part of the circuit. I turn the circuit on, I read my 6 amps, I call it a day, then I restore the circuit. Unless, of course, there's something wrong. All right, so now at this point, now that we gave you a little bit of a shakedown, you could go back and review that all you want, everything we've talked to this point. Let's go through the electrode. I'm not going to go agonizing over every little detail. I just want to give you a shakedown on the tools that are in the electrode so you don't feel so lost, okay? I'm choosing the module for air intake temperature sensor, just because it deals with a couple little different things here. Talks about the air intake sensor and is used to provide a sensory input to the engine control unit. In this case, temperature of the intake air. Knowing that air is necessary in order to determine the mass of the air drawn into the engine so you can gauge oxygen content and then adjust your air-fuel mix. The device the ECU uses to measure the intake air temperature sensor is called a sensor. It is not an actuator. Actuators act, they do things. Sensors sense, and they report information to the computer, okay? The control unit, the computer, uses air intake temperature to determine another quantity. What quantity is this? Up in here, it talks about just what I said, okay? That the sensor is used to determine how much air is coming into the engine, the mass of the air coming on in. It is, generally speaking, the sensor, a part of the mass airflow sensor. Sometimes it's a part like this one here, where it's all by itself. A lot of times it is in the same unit as the mass airflow. The intake air temperature sensor is located at the air inlet of the engine, usually between the filter and the throttle valve, okay, or throttle body. The electrical connector is accessible from the outside. The measuring part is not. That is, the measuring part extends through an opening in the air inlet where the measuring part makes contact with the air drawn in by the engine. Okay, so it starts asking questions about how the sensor relates to this diagram down here. I'll talk you through this here a little bit. Let me stretch this out a little, okay? So what number is the air intake temperature sensor in the diagram? So tip, look in the legend. Now, this looking down here, there's no way to see what's going on in this diagram, and then likely on your screen, this is probably gonna be really, really tiny or what have you, okay? So you could get this, drag it up here, take this, stretch it on out, get a better view of things, okay? Like this, if I wanted to maximize that, I could. So great, now I got a large viewing area that I could work with. Okay, so I want to know my intake air temperature sensor. Well, I'm not familiar with all these little symbols, let's say. I'm not used to seeing anything like this. It's a wiring diagram. I'm not used to it. It's basically a roadmap detailing the relationships of all the electrical components. What's talking to what voltage is going where, things like that. Okay, well, I'm sorry, what voltage is being applied where, and what direction currents are going and all that. And it said, look at my legend. That's what this is down here. So it tells you the details that relate to all these little numbers. I'm looking for my intake air temperature sensor. It says number 43. So that means that this component right here is my air intake temperature sensor. So now I could go ahead and shrink this back down. Look in the legend. It says 43. Check. Yes, everything's groovy. Boom. Which pin of the control unit is pin 1 of the intake air temperature sensor connected to? Which pin of the computer is pin 1 of the air intake temperature sensor connected to? Meaning, which wire goes from, I'm sorry, what pin of the control unit shares a wire with pin 1 of the air intake temperature sensor? So once again, expand this, stretch this bad boy out so you can look, okay? So now I'm looking for pin 1 of the air intake temperature sensor. That says 1 right there. This is my sensor. I know it's my sensor that I'm worried about because that's 43, and we look down here. So air intake temperature sensor, number 43 right there. I look up here at 43, and it said refer to pin 1. Okay, so which pin on the computer is between the sensor and the computer? So I follow my wire back up, and I get 35. Pin number 35 of the connector for the computer is what I'm interested in. Check. That's right. Click on the symbol of the air intake temperature sensor to view its location. So I click on this, and it's going to tell me where I could find this. Generally speaking, I will find it over here by the air intake itself. Where will I find the air intake temperature sensor on the car? In the inlet between the throttle body and the air filter. Correct. Shazam. Replace the air intake temperature sensor and connect it, then click check. This is a bit of a pain if you're not accustomed to it. So let's go ahead and zoom. Okay. Let's go ahead and look at our sensor because we found out where this was before. There we go. So we got to disconnect it by clicking on it. We get a hold of the sensor. Hold your clicker down. Drag it to the removed parts. Then you come back over here. Now, as you highlight it, you go replace this part. And it should turn yellow. And you can get it, put it back in, then reconnect that, and everybody's happy. Check it. Everything's fine. Special resistor is placed in the flow of the air in the opening of the intake sensor. The electrical resistance of this resistor changes as temperature changes. The housing of the air intake air temperature sensor is often made of plastic and has a mounting eye. meaning where a bolt will go through to hold it in, okay? A rubber O-ring prevents the engine from drawing in air that hasn't flowed through the sensor. So you have an O-ring right here to seal it up from the outside environment. Click on the sensor to view from the inside. So you click on the sensor, wow, we got this piece of metal, and the metal changes right here before it comes back out. So pin 1 and pin 2 of the sensor, and in between is a special resistor. Now a resistor has resistance, go figure. Okay, so that resistor has got resistance, and what happens is the computer will look at the resistance value of this sensor and make a determination of how much air is coming in based off of the heat. That being said, okay, resistance consumes voltage. Resistance consumes voltage. So what'll happen is, as the temperature affects the resistance of this sensor, the voltage that's being applied to the sensor and then going back to the computer will also change. Okay, so those two values can be figured out just by getting a simple reading by looking at the voltage signal, which is changed based off of the resistance that changes based off of the temperature that is applied to the sensor. Will let the computer know just how much air is coming on in, okay, or the temperature of the air coming in, better said. How many electrical terminals does this sensor have? 1, 2. You see them right there. Click. The following parts of the intake temperature sensor, mark them out. So you have your connections here, you got your special resistor right here, and you've got your housing right there. Click. Okay, so now we're going to play with the sensor a little bit and go over some of the resistance values. This is where the tool comes in handy. Okay. Sorry about the interruption, everybody. Okay, so here's what it's going to ask us to do. It's going to ask us to change the temperature that's affecting the sensor and then measure the sensor to check its different readings. Now, what it says is this type of resistor is called an NTC thermistor, okay? Negative temperature coefficient thermistor. Negative temperature coefficient thermistor. This means it is a resistor affected by temperature. And when it says negative temperature coefficient, that means that the heat and or cold, okay, will go opposite the resistance. That means the hotter it gets, the more resistance, the resistance will go down. The colder it gets, the higher the resistance is. Okay, typically a metal will go up and down in temperature and resistance together. They call that a positive temperature coefficient. This one is negative. So temperature and resistance go in opposite directions. So what is the resistance of this sensor at 0 degrees Celsius? First, we have got to set up our meter. So we're going to look at the resistance meter right here. We've got the ohm meter. It's plugged into ohms right here, common right here. So let's go ahead and drag our meter lead right here. Drag this meter lead and put it right there. Go ahead and move our meter. We're not going to be measuring in the millions of ohms, I don't think. Okay, 200 ohms? Possibly 2,000 or 20,000. Depending on the kind of sensor you have, you may end up dealing with thousands of ohms, all right? It's always a safer bet to start low, okay? Oh, there we go. Okay, you see this movement I'm making here? My mouse has a thumb wheel, a finger wheel on it. Okay, so as you use your finger wheel, that's gonna adjust that. If not, the clicker is gonna work. So let's start at 200 ohms. We're not reading anything. Let's go ahead and go right here to the dial gauge here. Go to 0 degrees centigrade. I'm hooked on. My meter's activated. I'm at 200. I don't see anything. So we click on this and we go up to 2,000. Don't see anything. Nope. When we get to 20,000 ohms, then we start seeing a value here. Okay. So that says 5. Now, 5 what? It's not just 5 ohms. We're in the range of thousands of ohms, kilo ohms. So it's 5 kilo ohms, 5,000 ohms. So the resistance of the sensor is 0 degrees centigrade is 5,000 ohms. Heat the air to 20 degrees. Notice that the resistance went down. Okay, that's what? 2,000 ohms, 2.00 thousand ohms, because it's in the kilo ohms range. By the way, this is going to get a little obnoxious with the way this thing does it. Heat it up to 40. How many thousands of ohms? Well, now I'm not on this side of the decimal, only have 0.5. Huh. Well, 0.5 of a kilo ohm is going to be 500, right? 500 ohms. Move. 60 degrees centigrade. Well, I'm starting to run out of room here, aren't I? Okay. 0.18. Okay, well, if this side of the decimal is indicating 1 kilo ohm, okay, that would put this at 18.18, meaning it's going to be 180 ohms, because we're dealing with thousands, go out to 3 places after. Heat the air to 80 degrees. Wow, we're really losing ground here, okay? We're looking at kilo ohms, 0.02. Something seems a little odd here. So let's go ahead and go here and then look at that value. See how it's going to change? Once you start losing a lot of digits here and you start getting into high decimals, you can go ahead and move your meter down. That is a little bit more palatable, I think. Okay, working in the 200 ohms range, and I see 20, or at least mostly 20. Good. Heat the sensor to 100 degrees centigrade. What is the resistance of the sensor? I'm looking at this and we don't see what this thing is averaging here. Given that we've been dealing with a bunch of round numbers so far, I'm going to go ahead and go with 1. Yeah, that's a little stable right there. So I'm going to go with 1 ohm. Check. Yes, that is right. How can I check the operation of the sensor? Manually heat the sensor and measure the resistance. We haven't talked about frequency. We haven't talked about current. This is resistance with a negative temperature coefficient. As my temperature increases, my resistance will decrease. Now finished, everything's groovy. Okay. So I just heard a weird beep for a while, so I do apologize if that's in here. I'm not going to go back again and record this whole thing over that one little beep. So there's a brief little shakedown for you. I hope it's helpful. And this is, I'm going to post this to YouTube, so let me know in comments if, good, bad, ugly. Please be polite and constructive if you're going to make a comment, please. I would appreciate it. So that is that. And I hope you sincerely all have a good Thanksgiving week. I'll probably post more of this style of video throughout the week for different kinds of content and what have you. Start building up our own little library of things. All right. So hope you have a good one. Take it easy.